All right, welcome back everyone to the topics of the week for Physics 8B. We are back after a really busy week last week. Midterm 1 is in the bag, and hopefully it went well or well enough. And now we can just continue and focus on Midterm 2. What's done is done, but I hope for all of you out there that it wasn't too terrible. And we have quite a bit to cover between now and midterm 2, it turns out, because the way the class is designed, basically it's going to feel like we're restarting from scratch with something entirely new, which is magnetism, magnetic fields in general. And it's going to seem for a while anyway that everything we've done we're going to forget about, even though some of it comes back later. And so we need to introduce magnetism, and in fact, I'm going to try to spend a little bit more time than I usually would on magnetism because it really dictates how good you feel about induction later on, because a lot of induction is based on magnetism, not exclusively. Obviously, induction is its own thing, but if you're confused about magnetism, it's going to be really easy to be confused about induction. So kind of mapped out the number of weeks that we have left between now and the test and now and the end of the semester, and it works out to me being able to do magnetism the first half today and the second half of it next week. And I'm going to purposely cut it into two parts because the truth is that the chapter really has two distinct parts to it. But it's really easy to not realize that if nobody shows you. So my goal is to emphasize that today and to say that, okay, well, the first half we're going to focus on today is going to be purely the magnetic force. In other words, what kind of force can you get from a magnetic field on a moving charge or on a bunch of moving charge, in other words, a current. And we're just going to focus on that. That's it. And then next week we're going to focus on how do you create magnetic fields from currents. And that's going to have some resemblance to how do you create magnetic fields with, electric fields, with charge. It's going to be a slice and dice method for magnetism called Biot-Savart. And there's going to be something that looks like Gauss's law in spirit, although it's very different mathematically, called Ampere's law that, makes it easy to find B if there's a lot of symmetry. And so I'm splitting it in two because if you think about it, when we did electric fields, we first just talked about electric fields and then we did Gauss's law, and there were kind of two parts, but all of it was about electric fields. And I think magnetism deserves the same treatment for clarity. So that's what we're going to do this week. Next week we'll do the second half, and then the following is going to be induction. And it should be such that by the time midterm 2 rolls around, we're slightly ahead of the coverage of midterm 2, so we should be okay. For those of you who are here for the first time, this is a weekly live stream to cover the topics of the week, and you can enroll for free in this course at slackademia.com. If you go to the study guides page, scroll to the bottom of the page, you can enroll in a free course called Physics 8B live stream, and you'll find all these live streams, the problems that I'm going to solve, along with the solved homework problems. Everything's in one course, so it makes it easy to navigate and find things. So with that said, let's maybe just give a quick overview of magnetism. Okay, so let's just divide the page in two here, and we're going to say magnetism 1 of 2, and then magnetism 2 of 2, and left-hand side is going to be today, and right-hand side is going to be next week. All right, so we're going to look at the magnetic force, FB, on a current, and on a moving charge, and then we're going to talk about, as a consequence of that, the motion of Q through B. Okay, that's the focus of today. That's it. So we're not really trying to figure out where do magnetic fields come from. I mean, we know they come from permanent magnets and currents, but we don't have any formulas in here that are going to tell us how to derive the magnitude of the magnetic field created by a current, for example. We're just going to say, look, oh, there's a magnetic field, okay. Here's the effect on the current and on just an individual moving charge. The magnetic force is going to act on that, and okay, then if it's just one moving charge, we can talk about how it is going to move through a magnetic field. Okay. And magnetism 2 of 2 is deriving B from a current I. And there's going to be two options. There's going to be Biot Savart, which is effectively slice and dice, and Ampere's law, which is like the, a distant cousin to Gauss's law in spirit. It kind of, you proceed in the same fashion when you're applying Ampere's law as you did when you were applying Gauss's law. But mathematically, it's something very different that you're doing. So just to be clear. Okay. So that's how I'm going to split it up, and I want you to, just realize or be cognizant of the fact that here we don't care where B comes from. Usually you're given B and you deal with it. Here it's all about how do you get B from the current, a distribution that you have. So is it a wire of current? Is it a sheet of current? What is it, and how does that affect the magnetic field that you get? All right, so let's start with, I'm going to start with the current. I know usually we start with the magnetic force on a moving charge, which seems that would make sense because then current is a bunch of moving charges. But I want to start with current because I want to group together magnetic force on a moving charge with how will that charge then move through a magnetic field. Okay, so just as a quick recap before we do some problems, we're going to look at the magnetic force on a current. Okay, so if you remember, electric fields can exert a force on a charge. Whether the charge is moving or not, it doesn't matter. Fe is QE. So as long as there's an electric field, if you put a charge in it, it's going to move. Magnetic fields are different. Magnetic fields can only act on moving charges. And even then, depending how the charge moves, you still might not get a force. But for sure, if the charge is just at rest, you're not going to get the magnetic force acting on it. Okay? So you need charge to move, which is why we look at currents, or just one point charge moving through B, but there has to be motion. Okay? So let's take current. All right, this is a wire of current like this. Current I. And this wire is placed in a magnetic field B. Now let's say that B points into the page. I don't know where it comes from, but I'm told there's a magnetic field B into the page. And it's the same everywhere. All right. Well, I'm going to get a force acting on this current that is going to be FB as a vector is IL cross B. And in magnitude, it's going to be FB is ILB sine of theta, theta being the angle between the two vectors L and B. Now, I'm writing it in vector form because, well, we need to explain what L is. L is the kind of the weird part of this formula, if you will. So let's go over this and just say that, okay, well, L is the length of the wire, and it's a vector that's in the direction of the current. So in this particular case, this would be L. Right. It's the length of the wire that carries the current, and then I is just the current itself. Okay? But you create that so that you have a vector with which you can do the cross product. And, well, the cross product is something we have to talk about because the force acting on this wire is going to have a certain direction that's given by the right-hand rule. Now, if you put 10 physics professors in a room and you ask them, describe the right-hand rule to me, you will get 11 different answers. Okay? So it seems like everybody has their own way of doing it. It seems that we're doing it for a whole bunch of stuff that's unrelated and we're not sure how it works or why it works the way it does. But all it is, it's a rule that's actually tied to a cross product. Okay, so it's actually a definition that could go back to math, where if you have a cross product, then the third vector, which is the result of the cross product of these two vectors, is going to be perpendicular to L and to B simultaneously, and in a direction given by the right-hand rule, which is just a convenient rule to not mess up the direction. Now, there's people that do it this way, with the three fingers kind of as the edge of a cube, a corner of a cube. There's people that do it this way. There's people that do it this way, or whatever they do, and they, align their fingers and then move the palm of their hand. Whatever. You can make up whatever nonsense you want. All of those versions are fine. But for the sake of simplicity, I will show you two different methods for the right-hand rule. I will show you one today for the force that I think is the best one to use to find the force. It's the easiest one, I think. And then next week, we're going to learn another one, which is just a variation of the right-hand rule, but is a lot easier to use when you're finding magnetic fields from currents, or the other way around. If you know the magnetic field, you find the direction of the current. Right. So the curling of the fingers around the thumb, that's for next week. I keep that specifically for that part of this chapter. The part of the chapter we're doing today, we're going to use the right-hand rule like this, basically like this, right, with our three fingers forming like the corner of a cube in a sense. And you have to be very careful. You have to align your thumb and your forefinger as if you were trying to form a gun, like if you want an imaginary gun. And then your middle finger has to point in toward the inside of your thing, toward the inside of your hand, right? So like this, right? So in other words, the two fingers are like this, but then your middle finger points toward the inside of your hand. I say that because I see a lot of students doing this, and you're not allowed to do that. If you're flipping someone off, you're doing the right-hand rule wrong, okay? So the orientation of your fingers matters greatly, and you have to have your thumb and your forefinger like this, and then the middle finger is pointing toward the inside of your hand. And the way it works is the same for every cross product. It's going to be the first vector of your cross product, which is L, along your forefinger. The second one along your middle finger, that's B. The angle between the two is theta, very often 90. In this case, it's 90 because B is into the page. And then your thumb will give you the direction of the force, which is the result of IL cross B. But the direction is the result of L cross B. Okay. So if I do that here and I put the forefinger of my right hand pointing northeast, basically, and my middle finger into the page, my thumb should be pointing somewhere in this direction. Okay. Now you might say, well, that's kind of approximate. Like, how do I know exactly the direction, or do I not? Is it kind of just that direction? No. Remember that FB has to be perpendicular both to L and B at the same time. So it's going to be in this direction, but very specifically, it's going to be in this direction, which is perpendicular to L. Okay? So that will be the force acting on the current. And so just to be clear, we have the only thing we have to introduce to apply this formula is L, which is has a magnitude which is the length of the wire, and then a direction, which is the same as I. Okay, but of course what it's doing, other than giving you the proper direction to apply the right-hand rule, it's accounting for the length of the wire, and the longer the wire, the greater the force. Okay. Now there is something worth noting, which is that if I flows parallel or anti-parallel to B, then there is no magnetic force. Okay, just to be clear, parallel means if this is the direction of B, the current flows in the same direction. Anti-parallel means that if this is the direction of B, well, the current is still aligned with B, it just goes exactly the other way, right? But, okay, in that case, you're going to have the angle between I and B is going to be 0 here. Here it's going to be 180, right, between these two guys. And, well, one way or the other, if you plug sine theta equals 0 into sine, you get 0. If you plug theta equals 180 into sine, you get 0 too. So even though there will be current and charge will be moving, you can still get no magnetic force if that current flows along B or exactly against B. Okay. So that's just for current. And I wanted to start with that because it's also kind of the simplest of the two when it comes to the right-hand rule, because current by convention is the flow of positive charge. So I need not worry whether my charge is positive or not. By convention it is. If I have a point charge though, that's a different story. It could be positive or negative. So let's look at the magnetic force. On a moving point charge. Okay, so I'm going to take a positive point charge, is going to be Q, and it's going to be moving to the right. With a velocity v, and there's going to be a magnetic field B. Let's take it into the page. All right. Now I'm then going to recreate the same scenario. The only thing I'm changing is that Q is now negative. All right. That's going to be a negative charge. So maybe I call it minus Q. That would be a nice way to designate a negative charge. Okay, well, a magnetic field can exert a force on a charged particle that moves through it, and that force is going to be given by FB is equal to QV cross B. So FB as a vector is QV cross B. FB in magnitude is going to be absolute value of Q, because Q could be negative, VB sine theta, theta being the angle between V and B. Okay, now this is a cross product, just like before, meaning that to find the direction of FB, we use the right-hand rule, just like before. The first vector of your cross product is going to be along your forefinger. Okay, so this is going to be V. The second vector, which is B of your cross product, is going to be along your forefinger, or your middle finger, I'm sorry. And the angle formed with the forefinger is going to be theta. That's the angle between the two. Most of the time it's 90 degrees. For example, here the angle between V and B is 90 degrees because B points into the page. And then here, your thumb is going to give you the direction of the magnetic force.
So let me maybe move this down real quick here. There we go. Okay. So that's the right-hand rule. If we apply the right-hand rule to the two scenarios that we have here, here I have a positive charge Q. If I put my forefinger of my right hand to the right, my middle finger into the page, hopefully you agree that the force FB is going to point up, and it will be perpendicular to V and B simultaneously by property of the cross product. And if I do the same thing with a negative charge, I have to be careful because my thumb, when I apply the right-hand rule, is going to wind up pointing up. Because of course V and B are in the same direction as in the scenario on the left. So, okay, my thumb points up, but it's a negative charge, so I have to somehow account for the fact that it's different. And it just means that at the end, once you've found that your thumb points up, you have to flip the direction of FB that you found. And flipping the direction of FB is acknowledging the fact that the charge is negative. Right? So you do the right-hand rule all the same, forefinger along V, middle finger along B, you get a direction for the force that's given by your thumb, and then if it is a negative charge, you're like, oh wait, final step, I got to flip it because it's a negative charge. Of course, if it's not a negative charge, then you don't have to worry about it. You're done, right? FB just points up in this case. All right, so that is the magnetic force moving on a point charge. Now we have a few important consequences here. The first one is that if V is equal to 0, then there is no force. So you can have a point charge that's at rest in a magnetic field, but nothing's going to happen. It's just going to sit there, right? You could even have a point charge that's at rest with no magnetic field. You flip the switch and you turn it on, and all of a sudden there is one. Nothing's going to happen. It's not moving. If it's not moving, then no force. Okay? Then if it is moving, but it's parallel or anti-parallel to B, then FB is equal to 0. So even though it's moving, if it moves in the direction of the magnetic field or exactly against it, no force acting on it. Okay? Then FB, by definition, is perpendicular to V and B simultaneously. So it will always be perpendicular both to V and B. And as a consequence, if your force is perpendicular to your velocity, that means your force is perpendicular to your displacement. That means that that force does no work. So FB, the magnetic force, does no work. And since it's been a while since 8A and work, remember that what work measures is how much kinetic energy, how much energy the force either provides the system with or removes from the system as the system undergoes a displacement. And the work done by a force will represent either the amount by which the kinetic energy increases or decreases as a consequence. Okay, so when we say that the magnetic force does no work, what we mean is that it cannot speed you up, it cannot slow you down. It cannot change your kinetic energy. Okay, now that's really important because it means that if you want to speed up particles, magnetic fields aren't going to do that for you. Electric fields are going to do that great, by the way. They're really good at it. We talked about that before. But magnetic fields, no. So something to keep in mind. Now, what magnetic fields are going to be great at is changing the direction of your velocity. It won't change the speed. The magnitude of velocity is going to stay the same, but it'll change the direction. Okay, and that's the next part that we're going to talk about, which is motion of a point charge. in a magnetic field. So, but this is an important property to keep in mind. All right? So I am out of paper, so hold on, give me a second here so I can add a page. There we go. Okay, so we were here, we wrote all that down. Let's now look at motion of a point charge in B. Okay, so let's say that we have a magnetic field that's into the page, created by we don't know what, it's just there. Some machine creates a magnetic field for us, and everywhere there's a magnetic field into the page on this sheet. Well, if we send a point charge q into this magnetic field with the velocity v in this direction, well, we can find the direction of the magnetic force. It's qv cross b. Forefinger pointing up the page, middle finger into the page. Hopefully we all agree that my thumb points to the left, and then this is going to be FB. Okay. Now what happens as the force pulls inward is that it creates an acceleration toward this direction, which causes the velocity vector to tilt. Right? But as the velocity vector tilts, then the force rotates with it. Right? So that's a little bit hard to see, so I'm gonna do it this way. This force creates an acceleration to the left. What a force does is it changes the direction of velocity. It could also change its magnitude potentially, although we just said not in the case of the magnetic force. So the magnetic force can change the direction of velocity. So it's going to want to rotate velocity like this, right? Take it and rotate it this way. The thing is, FB must always remain perpendicular to V at all times. So yes, it rotates V, but with it, FB rotates. And you can generalize this, and what you get is circular motion, where the force always points toward the center and is always going to be perpendicular to velocity, so you get circular motion when these particles are moving through a magnetic field. Okay? So in this case, we know that this thing is going to move along a circular path. We're going to figure out how to find the radius of that circular path, but it's going to be a circle like this. Is it a clockwise or a counterclockwise circle? Well, I know that the center has to be somewhere here because the magnetic force points toward the center, and I know the direction has to be counterclockwise because, well, that's the direction of velocity at that moment, so this charge is going to go that way. Okay, and if we do the mirror experiment with minus q instead, with the same velocity, okay, then we're going to get this. We're going to get a force that instead of pointing to the left is going to point to the right. And then we're going to get, because it's the same amount of, same speed, same charge, same amount of force, well, we're going to get a circular path that is clockwise with the same radius. Okay? So, in a sense, you know, it somewhat separates the charges. And I mean, if you let them go, they're going to go around in circles. But you know, if there's a wall with a hole here and a wall with a hole here, you can separate positive from negative. Okay, that's something that's done in a mass spectrometer, and we can talk about that later. But it's a classic exam question for that matter, and it's a very interesting application of magnetic fields for that matter. Okay, so it's important to know that if you have a magnetic field in a region and you launch a point charge in there perpendicularly to the magnetic field, that point charge is going to move in a circle. Okay, and we can in fact find the radius of this circle by applying Newton's second law for circular motion. So another memory from 8a. Right? But Newton's second law for circular motion goes something like this. It's the infamous F net R is equal to mv squared over r. And of course, F net R is the net force toward the center. It's the net centripetal force, because a force toward the center is what you need to move in a circular path. And then, well, that's going to be FB. Now, the magnitude of FB is absolute value of Q, V, B, sine of the angle between V and B, which is 90. And that's equal to mv squared divided by r. All right, well, this V cancels the square. Sine of 90 is 1. And I wind up with r is equal to mv over absolute value of qb. And that's the radius of the circular path followed by this point charge.
Okay, so it's a classic derivation. You have to know, first of all, that these point charges are going to move in circles, and then you have to know how to apply Newton's second law to get most of the time the radius, but of course you could solve for anything involved in this formula. The classic thing to solve for is the radius, though.
Okay, so let's do some problems. Let's start with this thing here.
Okay, and we have current flowing through a magnetic field. We want to find the net force on each wire. Now the first wire on the left
It's got this U shape to it, and then this one has this triangular shape. And we want to find the force on the entire wire, the entire U. But we have to be careful if we remember the definition of the magnetic force, right? If we remember that it's IL cross B, in other words, the magnitude is ILB sine theta, it's a function of L, and L is the length of the wire in a given direction. So you can't really say, oh, well, you know, I just have a wire like this, and so I'm just going to, you know, make all of this L. It's like, no, you can't do that. You have to break it up into 3 parts. Now, there is an interesting property that arises from this, and we'll talk about it at the end. But for the wire on the left, you would look at the 3 different sides, and you would say, okay, well, on the left side, I have current flowing up. Okay, so right-hand rule, forefinger up, middle finger out of the page. I should find that the force FB1 here points to the right.
If I do it again for the horizontal part, forefinger to the right, middle finger out of the page, you kind of got to contort yourself a bit, but
you get FB2 pointing down.
By the way, if you don't want to contort yourself, just rotate your exam, right? It'd be a lot easier. I could do it with my iPad, but you won't see it. So anyway, you get FB2 pointing down. And then if you do it again, forefinger pointing down, middle finger out of the page, then this will be FB3. Okay? And we would like to evaluate each one of these because we want to find the net force, so we have to add the x components together and the y components together and say what the net force is. All right, so for scenario A here, we have FB1 is going to be I times, I'm going to call this L1, I'm going to call 4L2, and so this is going to be I L1B sine of the angle between the current and the magnetic field, which is out of the page, so sine of 90. So it's I L1B. FB2 is I L2B, we'll sine 90 again because B is still out of the page and the current is to the right. So this is going to be I L2B, and then FB3 is equal to, well, perhaps, you know what, I'm just going to do magnitude. I'm not going to worry about signs right now. This is just magnitude. I L1B sine 90. Okay, so that's going to be I L1B.
And of course, I mean, we have to include direction if we're going to write F net x and F net y, but these are just the magnitudes of these forces. F net x is going to be I L1b minus I L1b, so that's 0 Newton. And then F net y is going to be minus I L2b, sine of 90 being 1. Okay, well, what is, let's see, B is 2 and the current is 2.5, so this is minus 2.5 times 4 times 2, which is 2.5 times 4 is 10, so minus 20 Newton. All right. And so the net force, if I want to write it as a vector, is going to point downward, so minus 20 y hat, and then Newton for the unit. Okay. So not too bad, right? I just have to realize that I have to take one side at a time, but then I write F net x and F net y, and I see what I get. Okay. So let's then do the same thing with this guy. And I'll bring this down here so I don't have to scroll up and down all the time. And this is 3 meters. This is still L1. This is still L2. The length here of the hypotenuse is going to be square root of L1 squared plus L2 squared, but with no surprise we get 5. It's a 3, 4, 5 triangle. And then if we do the same thing as above, then we can first draw the forces, find the components, and add up to F net. Okay. Current goes this way, right, along the hypotenuse, forefinger in that direction, middle finger out of the page. My thumb points in this direction. Remember that this direction is a very specific direction. It has to be perpendicular to the current. So this will be FB1 this time. And then for the right part here, well, this is just going to be I'll call it FB3 because it's the same as before, right? That piece is the same as the right side of the wire above. Okay. So I need components here, right? I need to find, because, okay, FB3 is along minus x, but FB1 is down and to the right, so it has x and y components. All right, so then this angle here, maybe I make this angle here theta, which makes this angle here theta, which makes this angle here 90 minus theta. Okay, now just for clarity, if I redraw my triangle here, this is a 4, 3, and 5 triangle. This is theta. Cosine of theta is adjacent over hypotenuse. That's 4/5. Sine theta is 3/5. Okay. And, well, let's give this a name. This 5 meters thing, I'm going to call that L. I'm going to do that because like that I can write the magnitude of FB1. It's going to be I L B sine of 90, which is 1. And then FB3, oh, no surprise there, it's going to be I L1B sine of 90. Okay. Now that's just magnitude, right? So that's not components necessarily. I need to work the components into this. Now if I want to write F net x, I'm going to find that the x component of FB1 here, perhaps I can zoom into it a bit, but this is going to be my vector, so this is my hypotenuse. This angle here is the angle between the hypotenuse and the adjacent side, meaning that the adjacent component here is going to be FB1 cosine of 90 minus theta. Okay, so FB1 is going to have an x component that is FB1 cosine of 90 minus theta, minus then FB3, which is to the left. Okay, so FB1 is I, L, B, and then cosine of 90 minus theta is sine theta, minus I, L1B. All right, that's going to be I, which is 2.5, L, which is 5, B is 2, sine is 3 over 5 minus 2.5 times 3 times 2. Okay, that's going to be 0. Oh, interesting.
F net x is 0 again. Okay.
Let's see what happens to F net y. Now F net y is going to be the y component of FB1.
It's going to be negative because it points down. It's going to be FB1 sine
of this angle 90 minus theta. So it's going to be minus FB1 sine of 90 minus theta. That's going to be minus I, L, B cosine theta, because sine of 90 minus theta is cosine theta. So that's going to be minus 2.5 times 5 times B, which is 2, times cosine theta, which is 4, divided by 5. And guess what? We get minus 20 Newton. And so the net force in this case is going to be the same. It's going to be minus 20 y hat in Newton. So 20 Newton downward is the net force on this wire.
And apparently it doesn't matter
Whether we have this or this, right?
which is interesting. But it's an interesting property of the magnetic force.
Right. So whether my current goes around like this with a wire that's bent this way or this way, the fact of the matter is it only matters that it started here and it ended here. Because here it started here and it ended here. Those are the same start and end points. Right. So in fact, I could generalize this. And I could say, now of course if I gave this on an exam, you'd smell a rat right away. You'd be like, that's too complicated, there's a trick. But it wouldn't matter if you did this with the wire, right?
It's the same start and end point. In all cases, the net force is going to be the same. So
what we'll say is that because in all cases we get 20 Newton net downward, irrespective of the shape. It's only a function of, there you go. It's only a function of these starting points and end points being the same. Right, so the same separation, they're aligned.
And so what we'll say is that it is as if
the current had just gone straight from here to here. Because if you draw these two things here, and you just draw a current I going straight across like this, which is the same as this segment here for that matter, well, what you're going to get? You're going to get 20 Newton pointing down. So what we'll say is that it is as if the current went straight from A to B, if this is A and this is B. Doesn't matter the shape of the wire from A to B. It only matters that in all four cases that I drew, A and B are the same. So it's an interesting property of the magnetic force, something worth keeping in mind because, yeah, okay, in these cases you can actually work it out. And it's a little tedious, maybe it takes a little bit of time, but you can do it. If something's a little bit stranger like this, then, well, maybe not. Probably not. You couldn't figure out the shape. But then there's an in-between where I know I give you A and B. I'm like, oh, look what I'm going to do. I'm going to do this. And I'm going to be like,
you're like, oh, I mean, sure. 1, 2, 3, 4, 5, 6 sides. So I have to do it 6 times. And then this is going to have X and Y components. Like, that's not fun. Right?
But if you know that all you need to do is say, well, forget the shape. It's as if I had this. So I'm going to just find the force acting on this. And it'll be the same net force as that which is acting on this. Then it saves you a lot of time to know that. Anyway, fun little property of the magnetic force on a current. Okay, let's do one here. Now this one, we're going to get slightly ahead of ourselves because I need a result from next week to be able to solve this, but I'm just going to assume that it's given and that, we're not going to understand it today, but, by the time next week comes around, it'll make sense. Okay, so if I have an infinite wire of current, it creates a magnetic field everywhere in the space surrounding it that is going to point out of the page above it and into the page below it. And in fact, it's going to circle around like this. And that's why it points out of the page above and into the page below. More on that next week. Okay, but for now, we're just going to accept that that's what it is. We're also going to accept that B1 is going to be given by mu naught I1 over 2 pi r. Very soon we'll know how to derive that with Ampere's law, but for now we're just going to accept it. R, by the way, is the distance from the wire. Okay, so what that means, and if you gave me this on midterm 2, I would know all of this, and this is what I would start doing immediately. What it means is that there's a magnetic field here at the location of the top wire that's different from the magnetic field at the location of the bottom wire because the bottom wire is further away from I1. So here I'm going to have a magnetic field, perhaps I'll call it B top, is equal to mu naught I1 divided by 2 pi d, because that's the distance between the wire and this top side of the rectangle. And it's going to be into the page. Okay, and then down here it's going to be into the page, but it's going to have a different magnitude. It's going to be B bottom is equal to mu naught I1 divided by 2 pi. Now the distance is going to be d plus big L. All right. And I need to know that because I need to be able to argue not just the direction but the magnitude of the magnetic field to find the force on each part of the rectangular loop. Okay, so if we take a step back, we have an infinite wire with current I1. The only goal of that wire is to create a magnetic field into the page everywhere here. And then we have this loop that carries a current clockwise. And just like in the previous problem, well, I'm going to have to find the force acting on this loop because, each segment is going to experience a magnetic force. And since the magnetic field is not the same everywhere, here it's a certain value, but here it's weaker, I'm actually not going to get 0 for the net force. I'm going to get a certain amount of force based on the fact that this is stronger than this, which we'll get to. But the logic is the same. If you tell me to find the magnetic force exerted on this loop, I'm going to take one piece of the loop at a time. Okay, so let's go ahead and do the right-hand rule. The current I1 flows through this magnetic field below the wire that is into the page. And so I always know the direction of the current and of the magnetic field. I can find the direction of the force. So we'll start with the top side. Forefinger to the right, middle finger into the page, the thumb points upward, this will be FB top. If we go to the right side, all right, forefinger points along I down the page, middle finger into the page. We're going to find that FB right points to the right. The bottom side here, forefinger to the left, middle finger into the page, FB bottom points down. And then if you keep doing this, you're going to find FB left like this. Okay, and we want the net magnetic force. Well, okay, by symmetry, if we think about it, whatever happens on the right side, the same thing happens on the left side. Like this force is exactly going to cancel this one. However, it is not true that this force cancels this one. The reason is, this magnetic field does not have the same magnitude as this one. So I cannot say that the current flowing through the top part here experiences the same thing as the current flowing through the bottom part here. That's not true. Right? But I2, as it flows here down the side, is going to see a magnetic field that decreases the same way that it then sees it increase on the way back up. The two forces are going to have the same magnitude. They cancel each other out by symmetry. Okay, so then the only thing left is to say, let's choose y as upward perhaps, that the net force in the y direction is equal to, well, FB top minus FB bottom. Okay, well, what is FB top? Well, it's the current I1 multiplied by the length of that side, which is W, multiplied by the magnetic field that it sees, which is B top, sine of the angle between the current and B top, which is 90 because B top points into the page, and then for the bottom part here, minus because FB bottom points down, I1, the same length W, however now the magnetic field is B bottom, and then sine of 90 because there's a 90-degree angle between the current and the magnetic field B bottom, which is into the page. Okay, so then we can sub in B top and B bottom, which we know what those are. That's going to be I1 W mu naught I1 over 2 pi d minus I1 W mu naught I1 over 2 pi d plus L. Okay, so we can make that a little bit prettier. It's going to be mu naught I1 squared W divided by 2 pi, and then 1 over d minus 1 over d plus L, which overall is going to be positive because 1 over d is a bigger number than 1 over d plus L, which means that this is an upward force with a magnitude equal to this. Okay, but that makes sense. You know, if you think about it, the only thing that distinguishes the two forces is the fact that this magnetic field is not the same as this one, and this one is stronger than this one because it's closer to the wire. So it's, I mean, I wanted to do it because, first of all, it's a super classic problem, and it's kind of borderline. I agree. You know, some of it will make more sense next week, but it's the same logic than the problem we just did, and it's just that this time we're already starting to see how you might combine. Well, one wire is here just to create B top and B bottom, and then the other one is just to carry I2 around. And so this is why I split the magnetism chapter in two, because, well, if you do everything at the same time, you might not realize what's going on. But really, you know, the way we solved it this week is just to say, I only care about currents going through magnetic fields. I don't care where magnetic fields come from? I have not learned that yet. Right? So if you give me a magnetic field like this and like this, sure, I can find the net force. Why not? But next week, we're going to know where this comes from because we're going to understand this and we're going to understand Ampere's law. And that's a separate part. It's give me a current, I1, that is there to create a magnetic field. I can tell you what the magnetic field is in magnitude and direction, at least in some cases. And so the point is, when you get problems on an exam, or if you just, if lecture doesn't really distinguish the two, then you have everything happening at once, which I personally find confusing, and apparently so do you, because I've been doing this long enough that it appears to confuse a lot of people, what current is doing what, and if I have multiple ones, it's important to distinguish what's going on. Anyway, so it's very similar to the one we just did. I just wanted to do it because it's a classic, and I'm not going to have time to do it next week because there's so much stuff to cover next week anyway. So just wanted to get it done. And again, if you revisit it after learning Ampere's law, you'll find that it makes a lot more sense. Okay, so we've done now two problems that involve currents flowing through magnetic fields and the force acting on these currents. And if the wire is bent, in different shapes or with different segments, we look at each segment, we can find the net force, and all that's fine. But we haven't talked about particles moving through magnetic fields, so that's the point of this problem here. Now, this problem here, we have two regions of space. They have the same magnetic field in magnitude, but the left region, B, points out of the page, right region, B, points into the page. And we know that if this is W, this is 3W. And outside of this region, there is no magnetic field except here, right? So if you look anywhere around here, there's no magnetic field. And we don't care how we created B out of the page on the left and B into the page on the right. That's just, somebody did that, great. I just want to focus on the force that this thing experiences. And so this is a proton down there, it's a positive charge, moving with the horizontal velocity just inside the bottom of the magnetic field of this region, which is into the page. And we're told, this is the key part, the proton eventually reaches the top edge of the two regions. So somehow the proton makes it to here. TBD how that's happening, but we're told that's what happens. Okay. And then if the proton is to stay within the two regions while it moves upward, what is the smallest that W can be? The width of that region. Okay. And then if we take W to be that width, then how much time does it take the proton to travel to the top edge? So this is a really clever problem. I really like this problem. Let's figure out what happens. Okay. Now we want to find the smallest W, the smallest width of this region on the right and on the left, so that the proton, when it's launched to the right like that, eventually reaches the top here. Okay. Now let's just first figure out what happens to this guy. Okay, it's a charge, positive charge moves through a magnetic field. We'll experience the magnetic force. Okay, it doesn't move into the page or out of the page, so there is going to be a magnetic force. And right hand rule, so forefinger to the right, middle finger into the page because we're in the right region, and then so B is into the page. And then my thumb is going to point upward. Okay, but remember we said that these particles, they move along a circular path, right? So this thing is going to go around a circular path, like this. Okay. Now, of course, I got to stop that right here because I'm not sure what happens once I reach this point here. But that's what's going to happen for there. And what do I know? I know that the magnetic force does no work. So the speed will not change. The velocity will change in direction, but the speed will not change. So it will arrive here with the same speed v0 just to the left. Okay, let's do it again. Forefinger to the left, middle finger out of the page now because b is out of the page. We still find that the magnetic force points up. So that means that this thing here is going to then travel like this. Well, I'm starting to see how it snakes its way up to the top edge, right? Because then the same thing is going to happen again, and so on and so forth. Okay. Now the thing is, this only happens as long as the proton remains within either the right region or the left region, because the only reason that it happens is the magnetic force is a centripetal force and pulls this thing along a circular path like this. So I need the magnetic force. If I don't have it, I can't snake my way up to the top edge. And so what I can't do is leave this region, right? If I go like this and then I leave the region, I'm going to just travel in a straight line because there's no more force to make me move in a circle. So how small can I make W? Well, the smallest you could make it would be so that you barely graze the edge right here. You're like, just on the edge, but then you turn. And if W is smaller than that, then you will exit the region with the magnetic field, right? You will exit right here. And from that point onward, you will travel in a straight line because there's no more force for you. So W cannot be less than this, right? Well, interestingly enough, that amount is the radius of the semicircular path. So hopefully that makes sense. If it's not, rewatch it again and convince yourself, first of all, that that's the motion of the particle. And of course, to have that motion, it has to be in the magnetic field. So I want W to be, wide enough on each side that it contains this path that we drew. Okay? So let me erase this so that we can draw this thing to scale. And what I'm going to do is say, okay, well, let's assume that this is now W min, and this is 3W min. Okay? Now this proton, if the width is W min, that is the width for which the proton just reaches the edge and grazes the edge and then, curves back in, right? So like this. Okay? And then I'll get rid of this part of the circle because it's kind of irrelevant. And then I'll say, well, do it again, yeah? So you make another one of these. And this is what we get. And there's value in drawing this to scale, right? Because it really helps me see what happens as the particle moves up. Okay, so my particle is going to snake its way up to the top edge like this. This is going to be a certain radius that I can find. And that will be my W min. Now to find that radius, recall that we write Newton's second law for circular motion with Fb, the magnetic force, being the only force toward the center. So by Newton's second law, I have F net R is equal to m v0 squared over big R, which is what I want. Okay, well that's Q, which is positive, v0, B, sine of 90 because B is into the page in either region, so it's always going to be sine 90. And this is going to be m v0 squared over R. And so just like we derived earlier, R is going to be m v0 over QB. And so W min is going to have to be equal to R. And so it's going to have to be M V0 over QB, at least. All right. So that's W min. And then if we take W to be W min, and so we have a drawing to scale to help us, how much time t does it take the proton to travel to the top edge of the regions? So how much time does it take the proton to do this? Okay, that's a great question. It is a question that I certainly don't want to answer with kinematics. That would be painful, okay, just because of the motion. However, I do know from 8A that when I have circular motion, particularly when I have uniform circular motion, which is circular motion at constant speed, which I have because the particle will move at constant speed, the magnetic force can't speed it up, can't slow it down. So when I have circular motion at constant speed, which is called uniform circular motion, I can define the period of revolution. That is the amount of time it takes to go around one full revolution. Like, okay, now I get it that that's not exactly what's going on here. The particle doesn't go around this circle here. But this part here is half a revolution. This part here is a quarter of a revolution. So overall, the distance traveled by the particle corresponds to 3/4 of a revolution. In other words, to 3/4 of its circumference of that circle. But the point is, if it takes me an amount of time, t revolution, to complete one full revolution, well, it's going to take me 3/4 of that time to complete 3/4 of a revolution. And so we're going to say that the particle, or the proton, travels 3/4 of a revolution to the top edge, which takes an amount of time delta t is equal to 3/4 of t revolution, where t revolution is the period of revolution. Right? And by the way, from circular motion, I remember that t revolution is 2 pi r, that's the circumference, divided by the speed at which I'm traveling. Because if I travel at constant speed, I can say distance over speed is time. That's okay. Right? So the conclusion is that delta t is equal to 3/4 of 2 pi r over v0, and I just found r. I said it's m v0 over qb. Okay, so remarkable property, v0 goes away. So the amount of time does not depend on v0, which is wild. And then I'm going to get 3m pi divided by 2qb. All right. So it's a really great problem. I really like it. It's very, very clever. It has all the properties of motion of particles in magnetic fields. You have to understand how this particle is going to move and how it makes its way to the top edge. You have to know how to find the radius. You have to know about the period of revolution. You even have to know that v0, the speed, won't change. And that's why, it's going to reach this point with v0. And so this portion here is exactly the same as this portion here, right? Because if it changed the speed, well, maybe that changes the radius. Probably does, based on the formula of the radius. So that would make things incredibly complicated. So it's a really great problem. If you understand it thoroughly and it makes sense, you're in good shape. But it's one of the best problems I've found to illustrate basically motion through a magnetic field without going crazy, because you can start to get crazy with motion of a charged particle through a magnetic field, especially if you want to add an electric field and so forth. Which of course is a great midterm question too, it's just a lot harder, and we're trying to get our feet wet here and understand the magnetic force both on a current and on a moving charge. So that wraps up what I wanted to talk about today. Again, I'm trying to, purposely make a break within the chapter of magnetic force first, magnetic field from a current next, so that you kind of compartmentalize the two in your brain and you recognize which problems come from which half. And then, okay, if we want to toss everything together into a midterm problem, well, you can untangle it and say, oh, well, this part is finding B from I. Then another current's going to go through that B from something else. Now I want to find the force. So it's, I found that I found that it makes more sense to do it that way for the most part. The risk of, we're so far into the semester already that usually the pace picks up, and once we hit magnetism, assuming we're not, behind on lectures, the pace is already pretty quick. Now, if you're behind and there's a holiday that, canceled a lecture or whatever, then it's even worse. And so professors end up rushing through magnetism, and that'd be fine, but not if the next chapter is induction, and induction is, it's better understood if you really understand magnetism, or at least you're comfortable enough with magnetism that you can then go ahead and have a look at induction and see how magnetism plays into it. So anyway, that was a long-winded way of saying that I purposely split the chapter in two. I don't usually do that for other chapters, but this one is really better off that way, I think. Hopefully that makes sense and kind of clarifies at least the magnetic force part of the chapter. As always, thanks for watching. I appreciate you. And let me know if you have any questions about this. If midterm wasn't so hot and you think you could have done better, or you would have hoped that you could have done better, feel free to reach out as well. We can talk about strategy. I'm not trying to sell you anything. I can give you advice as to, what to do next. Obviously, I tutor and all those things, so that's an option, but I'm happy to at least point you in the right direction. It doesn't have to be that you work with me or you pay me. Maybe it's just how you study or what you've been doing or what you've been studying that is off, and we can quickly course correct before midterm 2 is too close, because it will come fast, as you know. Once we hit midterm 1, everything just speeds up and is one after the other. So anyway, feel free to reach out for that. Thanks for watching. I will see you next week for the second half of magnetism. Take care.